Hello, we are from Group 6 of Exchange Student. We are going to explain our integrated design project on production of biodiesel from palm oil. And this is the content that we are going to explain further. So this is the process flow diagram of our biodiesel plant.
Moving on, the introduction of reaction engineering. So for the reaction engineering, we use the reactor type of CSTR or continuous stirred tank reactor because the advantage of CSTR, it has high conversion per unit mass of catalyst, low operating cost, and continuous operation. And for the reaction engineering, we use the catalyst of sodium hydroxide, which is heterogeneous catalyst that could work optimally at different phase from reactor or product. And for the reaction engineering, we have a few objectives here. The first, we have to produce valuable product of biodiesel or from palm oil. And next, to analyze the reaction of the transesterification process, determine the reactor sizing and the weight of catalyst needed to make the reaction feasible, propose the strategies to maximize the selectivity and yield of this product, and minimize the side reaction. And the last one, determine the economic feasibility of the whole process.
Okay, so the next one is introduction to separation process 2. We know it is important to remove all contaminants in the solution after undergoing a reaction to obtain high purity of biodiesel. And in this case, we've chosen membrane separation and evaporation as the separation process. And the objectives of this part of the project is first, is to design a suitable separation process system to improve the quality of biodiesel. The second one is to describe the mechanism of the selected separation process. The third one is to provide information of the separation unit material, type configuration, and the schematic diagram. And the last one is to provide the suitable calculation for the selected separation process with assumption and justification.
The introduction to process modeling and simulation. Here we have objectives to simulate the steady state reaction process, to validate the simulation by comparing with manual calculation, and to perform sensitivity analysis. The software used is
First is the catalytic reaction. From the feed inlet, we need to eliminate undesired products to get the most desired product. And it is a metal ester. So is highly demanded in the student industry for biodiesel and fuel industries. As you can see from the reaction, the feed inlet or the triolane can be reacted with methanol. It can be in the result of methyl oleate as the biodiesel. We need the most desired product, and set reaction of glycerol. Uh, Later, the glycerol will be removed with decanter or separator, so we can get a pure methyl oleate as the biodiesel for fuel industries. And next, for the reactor, we choose CSTR or continuous stirred tank reactor because on biodiesel production process, reactor temperature does not have a big effect because the effect of thermodynamic equilibrium of temperature is not very influential. And second, optimum temperature for the reaction is take place on 60 degrees Celsius because the energy impact that given by methanol molecules at the temperature is at its optimum, thus given more stable conversion. Because of this, we choose the CSTR reactor as our reactor in our biodiesel plant because of those two reasons, and also because continuously fed into the reactor at one point, CSTR, and the product of protein-reacted materials also continuous discharge from another point of well-mixed vessel. Moving on, for the catalyst, we use sodium hydroxide because in the transesterification, the process that react triglyceride in vegetable oils or animal fats with certain alcohols such as methanol or ethanol to produce FAME or fatty acids methyl esters. And glycerol as byproducts, the catalyst used is base or alkali and commonly used sodium hydroxide or potassium hydroxide. But for our plant, we use sodium hydroxide because commonly used for commercial production, relatively cheap compared to enzymatic and heterogeneous catalysts the other, and can speed up the reaction under mild condition and readily available in the market.
The next is strategy to maximize selectivity. Here, the reaction is as follows, and we can assume that is A plus 3B to 3C plus D. The desired product is component C, which is methyl ester, and then the desired product is the component D, which is glycerol. And we want the steps to maximize selectivity based on this case is first to decrease the concentration of the glycerol, and the second is to decrease the concentration of the methanol, and the third is to increase the temperature of the reaction, and the last is decrease the pressure of the reaction. The next is for the reaction sizing. We assume that first, the system is assumed to be an isolated system, where heat loss to the surrounding system is negligible. Second is we assume that the fluid flow is steady, which means in steady state. The third is the reactor is operated under plug flow condition without radial variation. And the last is we assume that the reactor is assumed to be isothermal, as a cooling jacket will be provided. For the reactor sizing, the calculation is first, we assume that triglycerides is A, methanol is B, methyl is C, and glycerol is D. Those direction will be as follow: mole balance of and the volumes the for calculation. The next is for the red law. It as follow: we want to know the red law, which is the reactants and the product. And the last is from the Arrhenius equation, with A equals to 2.25 equals 110 power to 15. We can get the value of K, which is 0.0125 per mole. Next is the reactor sizing. We know that the inlet composition for the mole fraction is as follows with the reaction below. Thus, we can make the stoichiometric table as shown below for the initial, the change, and the remaining, and the concentration of the stoichiometric table. The last is with the calculation of, we know that the initial flow rates, volumetric flow rates, and the initial concentration equals to 5.06 mole per second, 3.49 decimeter cubic per second, and also 1.68 mole per decimeter cubic respectively. We can get the value of, first we can get the final concentration of A, B, C, and D, and then we can determine the volume of the reactor. And here is the final value, which is concluded in the table as shown in the slides.
And the last one from reaction engineering, we calculate economic consideration for our reactor. It can seen from the table, we have 4 materials from the inlets: and palm oil, methanol, natrium hydroxide, and water. And with its price per kilogram and its flow rate, and overall cost for the material on the inlet is about 276.36 US dollar. And meanwhile, for the component, the products we result from the reactor or methyl ester or biodiesel, 1 USD per kilogram with a flow rate of 341.65 kilogram per hour. It can produce over 341.65 US dollar. So in the grand total, for the product we result and the component from the inlet, we can have a profit around 65.3 US dollars. So from the economic consideration, our reactor are feasible, so it can be used for the biodiesel plant.
Okay, so for the process modeling and simulation, we have to make the mathematical model for the reactor system. Here, we assume some parameters as stated. So we can obtain the model of mass balance, component balance, and energy balance as shown. After that, we simulated using symmetry program with parameter as follow, and the rate of reaction is considered elementary. So this is the result of the simulation of the reactor, and then from this we need to determine the deviation error in comparison of the manual calculation. So for the sensitivity analysis, we calculate the reactor performance in terms of triolein conversion, and the result is as follows.
Okay, so the next process that needs to be performed is separation, which covers membrane separation and evaporation. As we have mentioned before, it is important to have high quality biodiesel that has high purity, and therefore separation is one way to achieve that. And the details regarding these methods will be explained on the next slide. So here is the overall diagram of separation methods. And the first method is membrane separation, which aims to remove glycerol from biodiesel. This is actually a new method in dry washing, which is commonly performed by wet washing, such as decantation, settling, etc. And there are several advantages of using this method, such as it consumes less water, it produces less waste, which is more environmentally friendly, and it requires less time, space, and electricity. And this process will operate at 40 degrees Celsius and 1 atm. And this is several important information regarding this process. And this is the approximate sizing of the membrane. The material that is used is polyether sulfone, or PES, with the configuration of hollow fiber. And the reason why we chose to use this is because there have been many publications that shows promising results with this material and its configuration. And since we already have the data of solid rejection from a publication, we can construct a mass balance for this membrane separation. And the permeate will flow to the next separation process, which is evaporation, which will be explained on the next slide.
So this is the second stage purification of biodiesel. The evaporation, it is the evaporation. After the first stage using the membrane, now we use evaporator to separate the impurities that still contained in biodiesel. The evaporator is used to separate the solution based on its boiling point. The membrane it still have the impurities, so in this evaporator it will evaporate the methanol, water, and sodium hydroxide from biodiesel. The left double is the specification of evaporator that we use. We use the long to vertical evaporator with single phase effect type, and for the material construction we use carbon steel SE 283 grade C. The pressure condition is 1 atm, the temperature is 105 degrees Celsius, and from the dimension, its height is 1.4 meters, the diameter is 0.56 meters, and the thick is 0.18 meters. And for the head type is the tourist vehicle dish head. And this is the feature, the long tube vertical evaporator and single phase evaporator. It's from Jan Copley's 1993. Why we choose this type? Because the long tube vertical evaporator has a longer tube size when compared to other tube evaporator size. So it doesn't need too much space to take it. And then this type it has a good heat transfer coefficient, makes heat transfer process occurs greater, so it can increase the product from evaporator. And the last it has the low cost, so it can save money to produce the biodiesel. As you can see, this is the feed from membrane process that is from the permeate. It contains 0.1% of methanol, the 39.2% of sodium hydroxide, 38.65% of methyl oleate, 0.12% glycerol, and 21.2% of water. And as you can see, this is the data and the assumption that we must use for the calculation. The parameters is contain feed and liquid and the version of evaporator, TF, TBP, and etc. And this is the schematic diagram of evaporator, and this version is is from the membrane process that I explained before. And now this is the mass balance calculation. As we know, in the evaporation process, the mass balance for overall mass balance calculation is F equals to L plus V. F means feed, and L is liquid, and V is Weber. As I explained before, F is equals to 884.0686, and the liquid is 743.8. So we can get the vapor is equals to 140.16 kg per hour of vapor. And from our assumption, the fraction of evaporator is 60 is 96%. So for the calculation, for the methanol is like F equals to V plus L. The F for methanol is 0.9174, and for the vapor we must times with 96%. So we get the vapor value is about 0.88 kg per hour of methanol vapor, and for the liquid is 0.0367 kg per hour. And for the water, the F for water is 193.8, and for the vapor we must do times with 96%. So we got the value of V is 186.04 kg per hour, and for the liquid is 7.7 kg per hour. And the last is for sodium hydroxide. The sodium hydroxide is 100% evaporated due to the temperature operation occurs in 105 degrees Celsius. And for the boiling point of sodium hydroxide is below the operation temperature, which is about 1.388 degrees Celsius. And this is the summary methods in evaporator. As you can see, this is the inlet, this is the outlet, and for the component is contain the triolate, methanol, sodium hydroxide, methyl oleate, glycerol, and water. And this is the inlet or feed is from the membrane, and the outlet it contains vapor and liquid. And for our calculation, the methyl oleate that we get is about 97.48%.
So this is the mass rate from table before. The mass rate of methyl oleate equals to 341 kg per day. So for the calculation per year, we need two assumptions. First, the equipment operates 24 hours per day, and second, the equipment operates 5 days per year non-stop. So the biodiesel that we get is around 2,992,000 kg per year. So it can be concluded that it is same with the biodiesel required in this case, which is 3 million kg per year. Okay, so in conclusion, we have successfully designed full palm oil-based biodiesel plant in terms of reaction and separation process. And that's all from us. Thank you.